So in this video, I was interested in something more related to research, trying to take a look on on this method for training deep learning models without doing backpropagation. I found this article. There are a few other ones. This one is from the Victoria University in New Zealand by Wan-Duo, Lewis, and Bastiaan Kleijn. This article, basically in the same title, they proposed using this criteria for training the deep learning model without having to do backpropagation. This criteria is applied layer wise, but just you need a forward pass and just computing the gradient inside each layer. So as I said, yes, they're using the Hilbert-Schmidt independence criterion, and they frame everything in the information bottleneck or the information criteria world, and they propose this as an alternative to the backpropagation. So the idea of their approach is trying to build a criteria capable enough of reducing the dependence to the input data, but at the same time maximizing the dependence with the output. So for example, our task, we will frame it for now in a classification task. So each of the layers try to get the inner representation in which the dependence with the input data, which is our x, is the independence is maximized and the independence with the output is minimized. So making the most dependent possible to the output with the parameter that balance the influence of the dependence with the output. And this thing is made layer wise. They propose two training approaches. One, the informated training, is the one where we are going to use, which is basically apply this criteria for each of the layers, and the other one is adding an additional layer, for example, train it with like categorical cross entropy or the cross entropy for the specific task. And the pseudocode of the method is pretty straightforward. So we have our data, we iterate in batches, we do the forward propagation, the forward pass of the net, and then we just modify the layers, the parameters of this layer, just by computing the gradient of the criteria, combining the independence with the input part and combining the independence or dependence with the output part. This criteria is basically the Frobenius norm of the product of the kernel with the first thing and the kernel with the second thing. The kernel is centered and normalized. So it's not that, at least in a priori, so difficult to understand. So basically each of the layers is trying to find a representation that minimize this number. No, not this number, but this number, which in time is composed but 2 times this thing. For the kernel, they propose just a Gaussian kernel with the scaling also with the dimension, so they don't have to use a different sigma for different kernels if you are using the different size of the hidden representation each layer. They propose the theta as 500 and the sigma of 5, and for normalizing, just normalizing by the inverse of the matrix itself times the unity matrix by just a small constant. So okay, so this is a little bit of the introduction of the thing. Let's see if we can make it work, basically. I create a small notebook here in which I don't have done too much, just put here, just loading a dataset with MNIST. We are trying to make this work with MNIST. If we can make it work with MNIST, we are screwed. So we should be able to do it with this. And this is our pseudocode. I think we should start from here, and then let's see how far we can arrive. I was thinking of using jacks and flags and optags and the whole axe stack for doing this. So let's see. So I probably will start with this. So it's something clear that we must implement. So maybe we can start with the kernel itself. So we need the X and our sigma. We should compute exp the minus something like this times d. So let's create d is equal to x shape of 1. We can do, we need, no, I'm thinking of doing if this works, zoom x axis 1, no, this is GNP axis 1 from import JAX as GMP. This is our, so no, I think it's okay. So I have can I use a numpy matrix with this? Probably yes, huh? Yeah. Dot shape. Okay, this is reasonable. So we have our squares, and then I should do squared plus I need square transpose, but it will have some dimensional thing, right? So this is our S. No, okay. I am not completely sure about this. So if I put, let's go into check it, kernel X. We have something here. I'm not completely sure. Let's create kernel MP X sigma float. We have ND X shape. We have this. I think it's okay. Let's put it a D here. Let's put it just in case something like this, something like this. I'm not sure. And then we can return our K. Now it's creating from zeros, iterating blah blah blah, computing the Euclidean distance, and then okay, it seems reasonable. I don't think this is going to be equal, but maybe. Minus. No, because this is wrong. So my problem. problem is here, right? Because I have, so I need some kind of broadcasting of the values. So I need like an expand dim. Can I do JSP expand dims? Okay. Maybe I can do something like this. Should be a better way to do that, probably. Some. Okay, let's square. So this should be now a matrix, not a vector, right? Exactly. And then we have, okay, probably now it's probably correct. Okay, let's put what is our sum? It's still pretty high. So okay, I'm not completely satisfied with this, but we have a pretty clear approximation. So maybe we can send the kernel maybe we can move the... Ay, la concha de tu madre, por favor. Pairwise kernel, maybe we can... Let's put JMP array. No, JMP array is the type. Data matrix. Then we can just move it in here. Then we can move this to the test part. Let import numpy mp dev test kernel blah blah blah, and then we can import our pairwise kernel from here and import it. And we have at least, we have to import this thing. Okay, and we return an array. So okay, we have our kernel. Then we need to center. For centering the kernel, actually this guy shows centering. Is also a scikit-learn kernel center. So basically we should do this, which is basically the identity matrix and then the sum of rows and columns. So we are going to centering. So we can compute the f-center kernel. Okay, I do it automatically for me. 1 minus n np once exactly. But okay, thank you, Copilot. Okay, and we can move it also to here, and then we can GMP array, and then we can put it also here, and then we can return it. Okay, center kernel matrix. We can kernel matrix, centered kernel matrix, perfect. And then, so we have our pairwise kernel, our center kernel, then we can create a function center kernel, so we can compute our center kernel of our pairwise kernel. And we have something in there. And then the normalization. For the normalization thing, we can use this thing basically. So for the normalization part, normalize kernel, we are going to, is this times imb this thing plus an epsilon blah blah blah, and then I need the m, which is the shape.0. So this is something like this. Normalize the kernel matrix. This is GMP. It's NDR, yes. Probably yes. Return. Let's move it in here. Let's see here. The normalization thing was our center matrix times the inverse of our center matrix times the small value m and the identity of m, which is basically this thing. Okay. Normalize kernel. I think there should probably something with numerical stability there, but maybe not. It doesn't have imb. Okay, that's numpy. Line alg imb. Okay, so we have this. So finally, for computing our criteria, we need the trace of this product. Let's define, maybe then we can use it def n HSIC x GMP in the array y GMP in the array, and then we can return a float exactly. GMP trace, no, this is just our kernel x, kernel y. It's not data, it's data matrix. Probably I would like to have just the kernel. Normalize command. So this is basically a trace. So okay, this is x. Let's create a y. And then we can call our calling x and y. Okay, then we have a number. So the this number with the hidden representation and the input minus the hidden representation, the same criteria with the hidden representation and the output is the thing that we should optimize. Okay, we have this thing. So let's create so I was thinking something like this. Com layer, then we have to inherit from something, and then we have our class model. In our init, we are going to have for blah blah blah. Maybe we can do something like this. Let's do something like this. Like this. For let's put our input of features 3, and maybe we can create it. Okay, let's do something simple. Let's put pre features. Something like this. So pref feature is 1, 232, then it's going to be 32, and or maybe we can do. Okay, let's leave it like there. And then at the end, I would like to do some dense layer. We should compute how many features we have, and we can do it later with this is just for classification and classic. Then we can see if we can create something better. Probably here we can create a reshape or something like that. No, we can reshape it in here, so we don't create any problems. And then I would like to have okay, the call is just exactly forwarding, and then we have train step. We are going to receive x and y. We are going to do for. Okay, first of all, I need the maybe I can create a function in which I normalize centered kernel from the data, and then we can compute, and we need the sigma. We can x y this, let's call this so I don't know if I have to compute it here or in here. Let's see, I'm thinking about optac jax flux. No, not the split. There is a tutorial exactly. MNI's tutorial. Create an optimizer. Okay, we can create also here our optimizer, importing optacs. I think we have everything installed. Let's fix everything for now. We should have an optimizer, in this case, for each layer. So let's put self optimizers. Because this is going to be our single model, so we have like a single model. Self optimizers. Let's create something here. We have our learning rate, our momentum, everything fixed for all of the layers. Even let's something like this, or maybe just SGD layer NNX. What is NNX? Is exactly flux NNX. So we have our optimizer created for the layer itself, and then we need one for layer for the dense layer. I want this is optimizers. Okay, so maybe we can I have to list. This is just the first iteration of the code, and we can make it a bit better. And then we have the matrix. Maybe we can just compute it for the last layer. Maybe I should compute it for every layer, the matrix, but okay. And then let's create a model, blah 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 blah. We have our train step, our loss function. Okay, let's copy this. We have our model. So our loss function is, we should have here. Okay. How this is called in the train step? Batch train step model optimizer metrics batch. Model optimizer training batch. So we can call train step with our layer. So we can create just the zip probably with the layer and the optimizers. We use the optimizer in here. Let's just compute the losses for just in the last one. Metrics equal none. If exactly this metrics, and then I should pass. Let me think. So for computing this loss, I need kernel dx, kernel y for each of them, and our kernel set is enough. No, but I have to do the forward pass inside the train step, otherwise I have to do the training. I have to do the forward in here. Yes, I have to do the forward pass inside the loss function. So I need the previous input, and then I have to compute the kernel inside, I think. Previous input. Okay. So we have our train step in here. We receive the model, the optimizer, the metrics. This is at least it is easy. If metrics is not known, I will just update the loss. I think this is optional. I don't have roof installed, probably not. Format cell. So, and I compute value and grad of the our loss function. Our loss function has aux true because we return something. We should return it for the next iteration. So I need, okay, let's do the thing that we know. So the previous input. Then we compute, this is our okay, and then we have our loss, which is this thing, the product, the hidden with the x, the hidden with the x minus the, what is this? The hidden with the beta, that for now I'm going to hard code it as beta. And then I have to return our thing for the next iteration. And this is my thing for the next iteration. Is this okay? So let's recap. We have to implement this still. We compute the gradient as our function. Our function is just taking the previous thing, computing the kernel, computed our loss, returning our loss, and the thing, updating the optimizer, updating the gradients as the example here. Grads, which is grads, it's okay, taken from the model itself. So let's put in here printing things, at least we can see something. for now just print it. It's not like this is going to work at the first try, so self.metrics. No, but let's once we have, okay, yes. So I have to implement this thing. So I think this should be pretty reasonable to do. Let's, in the next module, def init self in feature of feature exacto blah blah blah. No, I prefer something like this. I have to also the random number generator. Okay. In features of features, let's keep it simple, and then we have our call, and then we can call a relu or something like that. We have a relu here, yes, something like this, pretty normal, not nothing crazy. In feature, a feature, we should compute. Okay, let's wait until the I have to use a relu here for the last layer. It can be just linear, no? Maybe we can leave it linear. And I would prefer to wait for the error to see how many features we need in the last one. So probably I can compute it, but okay. And the random number generator. How they create the model? Model is already created. Okay, here, thank you. We just can we can receive it also here. And using exactly and exactly. Okay. It's impossible to this thing to work, but okay, who cares? Okay, so we have this is our pseudocode. Let's put it in Markdown. Maybe we can move it upside. I don't know how to do it. Okay, let's create model. 2 layers, 10 classes. Model, train step, image level. Good luck. Of course, model is not defined. Okay. Oh, and exit not defined. What do you mean? Okay. Boom. Initial. No, what is that? You're right, because I forgot to add it. Has no attribute dense. And next, how is called here? NNX. Linear. Okay. Require one position argument sigma. Sigma we say 5. Let's create a variable here for our. This is shit, but then we can refactor a little bit if we after we get something working, otherwise. Okay. Another thing is when we are here, if x and dim greater than 2, x minus, so I would like to have 0 minus 1. No, if you have like an image, 32 image times something, time 64 by 64 by 3, we would like just flatten the image. So maybe we can X shape here. Exactly, we have this, we want this. There's another error in there. What is that error? What happened? Tuple index out of range. For the y probably, because it's just a number. So okay, if exactly, I don't like the x none. Let's put GMP expandims x1. Not the number in 5, 4. Oh no, there is a number. This number is increasing. Y is increasing. What is so negative, the number? Okay, chill. Let's create no, let me put it here. I can matrix. No, self no. So there's a few things that so clear this is not working. The question is why. So why do we have this increasing number instead of a decreasing one? So this is our loss in the last layer. I should remove the prints nevertheless. I should remove the prints in the middle because they're a bit annoying. Where is the print? Let's restart and run it all. Oh, XLA. Can we use just CPU? Solver internal error. What on earth do you want? Who is using 20%? Chrome is using OBS. But I'm using CPU for the dataset, right? Let's just in case. No. File to allocate. Why is trying to allocate that much? Oh, it's slow. So we have an increasing number in the loss. So it's so what is going on? What happened if we can stop it? Now every time the GPU enters running the KDE or something crashed. It's really uncomfortable to working like this. So we should move out from the notebooks. So this is dead. It's unbelievable. So we have 2 layers and the dense layer. We have an optimizer from each of the layers, basically, with a learning rate. We compute our criteria. We see the learning. This is this is just computing. Maybe we can interpret the loss as something like, because the value is increasing, maybe because it's increasing the association with the output. Can it be? Maybe we can print the 2 curves. Oh, what happened at the end? Let's see what happened if it's finished. What happened if I put something like this? No. Model images. I'm an idiot. What? We should. Okay, I'm an idiot. We should flatten. Can I flatten like this? Of course not. It should be a problem with the dimension. Exactly. Oh, what is so big? We have 32 times images.shape. 32 by 28 by 28 plus times 64 or 32. Yes. Can we not pad the thing and no, I don't want to same an XCOM. Let's try to reduce a little bit the dimensions, or maybe you can just make an average pooling. We have valid or circular. but the thing that we didn't have any dimension problems with the dense layer, this was an indication that something was wrong. Can we reduce, let's put instead of 32, let's put where is it, let's put 8, then we can flatten the thing. And for the matrix, I would like to have both metrics, so we should see one increasing, one decreasing, right? And this is the shape we have to hard code in here, then we will make something better, but I really don't care. Let's see. Dot. What happened? Dense layer and classes. 8. Oh, let's start from the beginning. So I'm flattening the thing and applying dense. Oh. Come on. Oh my god. No, and then I do this. 10 and 32. And 32. So there is something wrong with the dimension. Something wrong with the dimension in here. But it's going to, I think the problem is in here, eh? Ten, 1, 10 by 10. What is this 10 coming from? Labels. Where is this 10 coming from? Print. Guys, it's oh. Ooh. My god. Okay, how can I do X? It was just making the whole batch 2 dimension of 10. Okay, another thing. What is the problem? Okay. Dot general content. It is okay. Can we print in here x dot shape? 460. Oh, okay. Much more. The other dimension was also multiplying by 32. That's why it was so big. Oh my god, it was all along in front of my eyes. I'm tired. It's late. Okay, finally. Okay, let's remove every print. Let's keep it running. There's another print somewhere. In the kernel thing. Okay. Return. I think also this is correct because we have just one feature. We can just. I think it's correct. Oh no. Okay. And then we have to add the two losses, the independence with the input and the independence with the output, and see different direction in the optimization. Let's see. So how can I add some custom metrics? In the next metrics, can I add a custom metric? Compute. Base class. Any subclass should implement the compute, reset, and update. Compute and return the average. So I should call update. What is the update? The update in the train step, so I can update metrics update with the loss, and I can basically I can send kx, y, no? Maybe we can create our we can create our custom. This is completely frozen. Oh, please go back to life. This is terrible. I don't know if it's Kawin. It's back. It's back. Fail to discard change. Okay, don't worry. Now, if I do argmax, okay, beautiful. It didn't work. Which are the values in here? 0, 1, 2, 0, 1, 2, 3, 4, 5. It's the same value for everything. That's really promising, eh? Okay. Until we have something clear. It's not working. We can keep later failing. The next time I will try to create a matrix both from one side and the other side, at least to see if we can see something like this. So the dimension, the scale is a bit strange for me because we have really large values. So we see something in this range of 40. We are in super negative, so there is something that is not working. Maybe there's some scaling in some part that I'm missing. Okay. Yeah, but at least we have a x, y. This is a trace. I think this is okay. We have the x, the inverse, times m, which is basically this the batch size. We have the pairwise kernel. We are centering. We are normalizing it. Okay, a good failure. Let's see, last time. Strange that every image is with the same, exactly the same values. I don't know what happened at the end in here. Okay. Just a hiccup. But we have really, but I would like to see also from which of the two sides this value is so if it's so negative, it should be it's the same value for every image. Amazing. Okay, something is not working. Computing the gradient, previous input. We call the model, so we have the thing progressing. Times x, time y. Normalize x, normalize y with our sigma. Our previous input, the previous becomes the new one. Layer is layer, optimizer is optimizer. Okay, a good failure. I'm sad but happy. Let's see the next time if we can work it out.